Hello, and thank you for coming to my talk. Today I'm going to be telling you a little bit about some work I've been doing over the past year or so in collaboration with Marco Bruni and John Barrow. So the subject of my talk will be an alternative to inflation called bouncing universes, and we shall be talking about whether these universes can undergo the isotropisation process and in fact end up bouncing. So let's begin. We should start with talking about the dominant or the most discussed paradigm of the early universe called cosmological inflation. Now, this does very good things to us, and we will quickly go over what those things are, and then we'll discuss a few issues with the paradigm, which led people to look for alternatives, such as the bounce. After describing what the bouncing paradigm entails, we shall talk a little bit about why the growth of anisotropies is a problem for this paradigm. And we should talk about a mechanism that people in the community have been using to deal with this issue called Ekpyrosis. We shall talk about a stumbling block to Ekpyrosis, a possible stumbling block, and that is the inclusion of anisotropic pressures. And then in the next section, we shall see how these anisotropic pressures can in fact be used to our advantage and help us in the process of isotropising this bouncing universe. And finally, I'll give you some conclusions. So, cosmological inflation. Now, this diagram must be something that you're very familiar with. You must have seen this before. It just represents the history of our universe as we know it, right from some theory of the very early universe and starting in a Big Bang, which could be inflation, and then ending up right at the present day dark energy dominated accelerated expansion of the universe. So for the remainder of my talk, I will really be focusing in this region of the history of our universe. Now, cosmological inflation can be described as a period in the history of the universe which underwent accelerated expansion mediated by a scalar field whose dynamics were dominated by its potential. So the scalar field was slowly rolling. And this sort of dynamics is able to explain a lot of the problems of standard Big Bang cosmology. So what can inflation do for us in resolving the problems of standard Big Bang cosmology? For example, it can give us a causal mechanism for the formation of structure. It is able to resolve the horizon problem by hypothesizing an exponentially expanding past horizon so that the past light cones of seemingly causally disconnected patches of the CMB sky intersect. So this would give us an explanation as to why these disconnected patches of the CMB sky, causally disconnected patches of the CMB sky, have such small temperature variations. It is able to explain the isotropy problem. Now, anisotropies typically grow as 1 over volume squared. So in an nearly exponentially expanding cosmology, these anisotropies, or the energy density in these anisotropies, would be redshifted very, very quickly. It's able to explain the flatness problem, a nearly exponentially expanding background, which you can approximate as a background dominated by a nearly ideal equation of state, is very able to explain a nearly scale invariant scalar and tensor spectrum. By the way, at this point, it's worth noting that a scale invariant spectrum of scalar and tensor perturbations, along with the Sachs-Wolf tail and the baryon acoustic oscillations that we see in the CMB, can be explained by a superhorizon spectrum of scale invariant adiabatic perturbations at matter radiation equality. So this was found by Peebles and Yu, and separately by Zeldovich in the 70s. So, I mean, inflation is not the only theory that can explain these features of the CMB, but it is able to give us a primordial mechanism for the generation of such an adiabatic scale invariant spectrum. And finally, it predicts very small non-Gaussianities, and we haven't really had any conclusive evidence for non-Gaussianities today. Despite all of these successes, unfortunately, there's always a but. And it is this but that leads us into the subject of my talk, into the search for alternatives. Before that, let's quickly discuss what issues this paradigm faces. So for example, and this is the one that upsets me the most, is that an ever-expanding cosmology must, by the Hawking-Penrose singularity theorems, have started when extrapolated backwards from an initial Big Bang singularity. So there's no way out of this problem, and I think, the general wisdom is that some complete theory of quantum gravity should be able to resolve this initial Big Bang singularity. There's a trans-Planckian problem, which briefly means that any wavelengths of cosmological interest today would have had to originate in a region of space-time or at an energy scale where one could no longer trust perturbation theory for these wavelengths. The exit from inflation is a problem. No one really knows how to stop inflation once it starts, and we need about 50 to 60 falls of inflation to explain the observations of our current universe. Also, it's not clear how one can successfully reheat the universe to the hot Big Bang from the end of inflation. A related problem is the presence of eternal inflationary scenarios, and in certain theories, one might end up with some sort of a multiverse realization. The eta problem, which basically states that if you have large field inflation, then the distance traveled in a field space by the inflaton would mean that it accrues quantum corrections which are so large that it would ruin, for example, the slow rolling behavior, which is so necessary for inflation. The paradigm suffers from quite a few initial conditions problems where it's not clear why we need such specific initial conditions to even start the scenario. And there are various fine-tuning problems around just too large quantum corrections. And I think another thing that really disturbs me about the paradigm is that there are so many model realizations of it that it sometimes to me feels like you could have any sort of observation and come up with a model realization for it within the inflationary paradigm. And it's really hard to prove something right if you can't prove it wrong, if you know what I mean. And so on. So all of these issues, they really prompted us to look for alternatives. There are several motivations for doing this. For example, while it's important to focus model building efforts within the inflationary paradigm, it might, even if you are a strong believer in the paradigm, it is important to study alternatives and prove conclusively that the good things, that the predictions that inflation is able to do, that the problems of standard Big Bang cosmology it is able to solve, in fact, cannot be solved by any other model realization or any other model that you can conceive of, or that is different from inflation. Also, there is a school of thought which says that you can't really correct the problems of a paradigm by sitting within the paradigm. And it's important for you to step outside of this paradigm and look for other alternatives for you to be able to successfully correct the issues within it. So all of these reasons, whether or not you are convinced by the inflationary paradigm or not, I think it's important for us to focus some of our research efforts into studying alternatives and seeing whether we can build successful models that match with observational predictions today. So let's recap for a little bit. We've talked about inflation as a theory of the early universe, which is just a scalar field mediated accelerated expansion in the very early universe. It does really good things for us. For example, it solves the horizon flatness problems, isotropy problem, gives us a primordial mechanism for generating scale invariant scalar tensor spectra, predicts small null Gaussianities, gives us a causal mechanism for the generation of structure. And despite all of these successes, it does have certain issues. For example, it is plagued by the presence of an initial Big Bang singularity. There are issues relating to fine-tuning and the problem of initial conditions. It's not clear whether we can trust perturbation theory right up to the scale of energy scale of inflation. There are issues regarding stopping inflation, reheating the universe, etc. And we have just said that given all these issues, it is important to study alternatives, not because inflation is a paradigm that is intrinsically incorrect or a worse theory of the early universe, but because sometimes it is useful to study alternatives to correct the paradigm that we are trying to improve upon, that is to sit outside of the paradigm. Also, if we are able to prove that none of these alternatives can be successful models or achieve some similar degrees of success as inflation, then we can have some degree of more confidence in the inflationary paradigm and then try to make it better. So regardless, I think it's really important to study alternatives. And today we shall be studying one such alternative, that is the bounce. Before I begin talking about the bounce, I think it's important for me to say that it is not the only alternative that people have thought about. For example, very early on, people considered the symmetries that arise in string theory called the T-dualities to hypothesize the presence of two non-equivalent dual solutions of cosmology, where one solution corresponded to an expanding universe and the other to a contracting one. And this was a precursor very much of the current bouncing scenario, because these two dual phases were stitched together at, at the bounce in this case by something called an S-brane, which is an object with zero energy density and negative pressure. So it explicitly violates a null energy condition because rho plus p is negative. And this model was not very successful because it didn't really give us the right scale dependence of the spectra that we needed. But it was important because it served, as I said, a precursor for developing the ideas that led us to the current bouncing paradigms that I've been studying. There's another alternative called the string gas cosmologies, which hypothesized that the universe was static and it was sourced by a hot gas strings, and it exploited the thermodynamic properties of these string gases. That is, it used the fact that these string gases would undergo a phase transition called the Hagedorn phase transition, so that this static universe would then suddenly start to expand. Today, though, we're going to be talking about a different alternative, and this alternative is called a bouncing cosmology. So a bouncing cosmology describes a universe which was initially contracting. And as the universe contracted, it reaches a minimum size. And at the minimum size, it starts to re-expand again. And we happen to be living in the expanding bit. Now, there are many, again, realizations, as we shall see, of these bouncing cosmologies. There are people who study singular bouncing cosmologies, that is, the size seems classically zero, but in a quantum theory, of course, there would be some minimal length scale. And quantum effects would contribute to the new physics that we must necessarily inject at the bounce to cause this re-expansion to occur. I am interested, however, in classically non-singular bounces because my main motivation for studying bouncing cosmologies is to get rid of the initial Big Bang singularity. So for me, the price I pay for getting rid of this singularity is the injection of new physics at the bounce to cause this re-expansion, or in certain cases, spatial curvature. So what do I mean by that? In order to understand that, we'll have to think about what are the conditions for a bounce to occur. So we can think about this very simply. Let's just think about this in the context of the Friedmann equations. As I said, we are starting out initially contracting. So in this contracting phase, the Hubble rate has got to be negative. For similar reasons, in the expanding phase, the Hubble rate has got to be positive. So in the transition or the bounce phase, the Hubble rate has got to go through zero. So that's our first condition. Hubble rate is equal to zero. The second condition is that if we want our universe to start expanding again, then h dot, or the time derivative of the Hubble rate, has got to be positive, right? So if we look at the Friedmann equations, h dot is given by k over a squared minus half rho plus b. If we don't have spatial curvature, that is, if k is zero, we don't have this term, then we're just left with minus half rho plus b. So for h dot to be positive, rho plus b has got to be negative. And this is what we mean by the null energy condition violation. So in the absence of spatial curvature, you have to have some new physics which violates a null energy condition, albeit for a very short period of time, for you to execute a successful bounce. If we have positive spatial curvature, of course, this is not that much of a problem, but there is a little bit of controversy around the idea of whether we can indeed have whether we indeed have a non-singular bounce, even if we have a successful bounce, in the presence of positive spatial curvature. It might be that we need to include some other effects for the bounce to be classically non-singular in closed or positively curved universes. So before we go on to discussing what ingredients we can put in our bouncing model, let's see how these paradigms are doing in solving the problems of standard cosmology. So if we use the fact that as the bounces approach, h tends to zero, or if we say that our initial contracting phase lasted from t tends to minus infinity, because we have no knowledge of any previous phase, then the horizon, when we don't have a horizon problem, because the horizon is always large enough so that all of the modes of interest today would have originated sub-horizon. Non-singular bouncing models automatically, by construction, would be able to solve the initial Big Bang singularity problem. And this, to me, is their most attractive feature. What about the homogeneity problems or the curvature problems? It's not clear. It's not clear whether, if we start out with the perturbative inhomogeneities that we need to successfully source large-scale structure in our universe today, whether those perturbations would actually grow to full inhomogeneous modes in the contracting phase, which would then somehow ruin the bouncing behavior or would not allow the universe to re-expand. Curvature seems to not be a problem in the contracting phase because it grows the least quickly compared to any other energy component. But it might be that curvature becomes a problem at the bounce itself. And this is something that I'm trying to study at the moment. What about isotropy? What about growing anisotropies? And that's what we're going to be discussing in this talk. So what are the theories of the contracting phase that people have studied? Well, one theory is called Ekpyrosis. And this is a theory that describes a period of slow contraction mediated by a fast rolling scalar field. Now, this scalar field would be rolling very quickly down a steep negative exponential potential, and effectively it would behave as an equation of state with pressure much greater than density, or W much greater than 1. And this equation of state is called the ultra-stiff equation of state. And as we shall see later on, this shall be instrumental in dealing with the isotropy problem. Now, Ekpyrosis does very well in dealing with anisotropies and inhomogeneities, but unfortunately it ends up predicting a blue-tilted spectrum of scalar perturbations, at least in the single field case. So you would have to introduce an extra degree of freedom, like two-field Ekpyrosis, for example, for you to be able to have a scale invariant spectrum. The other theory is the matter bounce, where the contraction is dominated by a matter-like fluid or a fluid that behaves like dust. And this exploits the duality in the power spectrum of scalar perturbations to the duality exists between an exponentially expanding background or a dust-dominated contracting background to predict a scale invariant spectrum of scalar perturbations. The issue with the matter bounce, of course, is because it does not have the advantages of the ekpyrotic universe of having pressure much greater than density dominating its dynamics in the contracting phase, that this scenario is plagued by the problem of growing anisotropies. So how do we get a bounce then? There are lots of, as you can see, there's an exhaustive list of how one can get a bounce. The key takeaway from all of this is that whatever ingredients you put into your universe, you have to be, this key ingredient in the absence of spatial curvature has to violate the null energy condition. In the presence of spatial curvature, the situation is not as dire. So for the purposes of our talk, we will be using alternative number 3, as we shall see in the next slide. And there are many, and I shall not go into the details in the interest of time about what each of these theories are. So in our talk, we shall be exploiting a non-singular cosmology which is sourced by a nonlinear equation of state. This just means that we add a quadratic term to our equation of state, and this quadratic term is divided by an energy scale ρc, so that this nonlinearity in the equation of state becomes important only when the energy scale of the universe is close to ρc. For our purposes, we shall be choosing the linear term to resemble radiation, that is alpha should be 1/3, and we are choosing beta to be -1 because we have seen that it has been shown by Kishore and Marco that oscillating solutions can be found in the isotropic closed Friedmann-Robertson case with this choice. And this corresponds also to something that has been studied in loop quantum cosmology models as well. So let's recap a little bit. And to recap, I'm going to use one of my favorite authors. His name is Douglas Adams. And if you haven't read The Hitchhiker's Guide to the Galaxy, this is a great time for you to read it during quarantine. So he says, the story so far. In the beginning, the universe was created. This has made a lot of people very angry and been widely regarded as a bad move. So the question that we're going to ask in our talk is, do anisotropic bouncing cosmologies, are they still able to bounce and isotropize? And to be able to answer this question, we're going to have to see why anisotropies are a problem in our contracting universes. To do this, let us consider a really simple example. In this example, we have a flat anisotropic universe where the universe is just expanding differently with different rates in the three different directions. Now, the effective Friedmann equation is given by this, where the energy density in the anisotropies is encoded in sigma squared. Now, the shear evolves according to this evolution equation, and we can see that sigma squared, which is sigma alpha beta, is going to evolve as 1 over volume squared. Now, for a contracting universe, 1 over volume squared is something that grows faster than any other energy component. And therein lies the issue. So this means that any sort of the matter field that we include in this in our model, which in our case, of course, with the ekpyrotic fluid, would need to have an equation of state pressure much greater than density, because then this would allow this matter field to evolve faster than 1 over volume squared. So, of course, it's not enough for us to just study cases of expansion anisotropy. So to generalize this further, we generalize to a particular geometry, which includes not just expansion anisotropy, but also anisotropies in the 3 curvature. Not only does it do this, it is also a generalization of the closed Friedmann-Robertson-Walker universe. And if we do not want to violate the null energy condition, then our best bet is to try to include positive spatial curvature. But if we want to do this, then we have to answer the question as to what happens when we add anisotropies. How much are we able to isotropize a closed anisotropic universe? And this closed anisotropic universe has anisotropic 3 curvature. And the issue with anisotropic 3 curvature is that it shows a very interesting behavior by which it undergoes chaotic Mixmaster oscillations, which are infinite in number on a finite time interval. So any theory of the early universe that is able to explain the isotropic problem should be able to mitigate or remove this chaotic behavior. So let's see what happens when we include this nonlinear equation of state in this general closed anisotropic universe. We see that despite the presence of this rho square term, which technically should act as a pressure much greater than energy density term, it's still not able to isotropize this anisotropic universe. The scale factors still undergo these chaotic oscillations, and they show no sign of becoming more isotropic. So clearly we need another ingredient. The situation gets a bit worse, because if we are to include anisotropic stresses, which if we want to study anisotropies in total generality, we should include anisotropies not only in the gravity sector, but also in the matter sector, which would manifest itself as anisotropic stresses, then we see that the shear equation of motion, even in the case of the flat anisotropic universe, is sourced by these anisotropic stresses. So this shear equation so the shear anisotropies in fact grow faster than 1 over volume squared. So any ekpyrotic fluid that you would have to include would have to be able to fine-tuned. First of all, it should not have any of the anisotropic stresses, and it would have to be fine-tuned to be more stiff than these anisotropic stresses. And sure enough, when we look at the situation of what happens if we include ekpyrotic fields with anisotropic pressures in the Bianchi type 9 universe, the anisotropies grow. So much so that the bouncing behavior itself is destroyed, and this universe collapses. So the situation is not lost, because we can actually use anisotropic pressures to our advantage. If we use negative anisotropic pressures, especially of this form, then they actually take a very familiar form. They take the form of shear viscosity. And shear viscosity has been shown to damp gravitational waves in the late universe because of the presence of neutrinos. And we can use the same principle, because it's very reasonable to expect viscous effects in the tightly coupled plasma that must have existed in the very early universe. So these viscous effects actually do have the same effect on these shear anisotropies. The shear anisotropies, the normalized shear and energy density in the anisotropies, begins to fall when we include these these negative anisotropic stresses in the case of Bianchi type 9. And if we look at the evolution of the scale factors, indeed, the scale factors seem to become more isotropic and their chaotic oscillations are mitigated. Studying the Lyapunov index, we indeed see that we get more evidence that this chaotic behavior is in fact mitigated with the inclusion of these viscous stresses. So we see that actually we are able, that we can take a few take-home messages from this. We can show that a Big Bang singularity does not have to be the end of our story. Nonlinear fluids can source a bounce, but unfortunately, nonlinear fluids alone are not able to generate isotropy. Another way that we can come up with a successful isotropisation mechanism is by including dissipative shear viscous effects. And the good thing about these is that it does not have the same pitfalls as the ekpyrotic scenario might have in terms of not being robust to positive anisotropic stresses, and in certain cases not being able to create a scale invariant spectrum of scalar perturbations, and also in having issues with an instability caused by the growth of the kinetic energy of the scalar field, because it was a kinetic energy dominated evolution down the negative exponential potential. So we don't have to deal with any of these if we just include viscous stresses, which is very reasonable to expect in the very early universe. And with that, I thank you for your time.